Bismillah ar-Rahman ar-Rahim. We are interested in minimizing a function f of x. F is a function from Rn to R. F is a differentiable convex function. Its gradient, which is the vector of partial derivatives, is Lipschitz continuous. There exists a finite positive real number L, such that for every x and y in the n-dimensional space, the L2 norm of the difference between the gradient vector computed at x and the gradient vector computed at y, this L2 norm is upper bounded by this L times the Euclidean distance between x and y. If we minimize f of x using the plane gradient descent algorithm, the rate of convergence is of order 1 over n. Suppose that f of x has a minimum at x star. Then f of xn minus f of x star. This is the value achieved after n iterations or n steps minus the minimum value. This difference is upper bounded by some positive constant over n. If we use the accelerated gradient descent algorithm, this difference here will be upper bounded by some positive number divided by n squared, not n. Here is the algorithm. The step size or learning rate parameter eta is strictly positive and is less than or equal to 1 over L. L is the parameter used in defining the Lipschitz continuity of the gradient vector. We have a sequence of scalars, g0, g1, g2, and so forth. g0 is equal to 1. At each iteration, we update two vectors, x and v. X is randomly initialized. V of 0 is equal to x of 0. In the kth step, we update vector x using this expression here. X of k plus 1 is equal to v of k minus eta, the gradient of the function f evaluated at v of k. This is what we have here in the accelerated gradient descent algorithm. In the plane gradient descent algorithm, rather than having this, we have a straightforward update expression. We have x of k plus 1 equal to x of k minus eta times the gradient vector evaluated at x of k. This is the conventional gradient descent. In the accelerated version, we do the update using this vector v. How is vector v updated? We first update the sequence of scalars. Gk plus 1 is equal to 1/2 plus the square root of 1/4 plus gk squared. Using this, we update vector v. V k plus 1 is xk plus 1 plus xk plus 1 minus xk times gk minus 1 over gk plus 1. V of k plus 1 is some linear combination of x of k and x of k plus 1. The linear combination depends on gk and gk plus 1. In this video, I focus on the convergence proof to show how carrying out such an algorithm will lead to a result with n squared here rather than n. While doing the proof, we will have an idea why we have these two update rules. As I said earlier, that f of x attains its minimum at x star. There are two inequalities that are very important in our investigation. The first inequality is a consequence of the convexity of function f. If function f is convex and it has partial derivatives that are continuous for every x and y in the domain Rn, f of x is greater than or equal to f of y plus the inner product between the gradient evaluated at y and x minus y. So this is the transpose. Our default vectors are column vectors, and so to convert a vector into a row vector, we do transpose. This is an inner product. Specifically, this is the summation I from 1 to n, the partial derivative of f with respect to yi, xi minus yi. By this, I mean that we take the partial derivatives and they are evaluated at the point y. Because the function has a gradient that is Lipschitz continuous, there is another inequality that we can employ, and it depends on the parameter L. This other inequality is that for every x and y in Rn, f of x is inferior to f of y plus the inner product of the gradient and x minus y plus 1/2 L times the Euclidean distance between x and y squared. That is the L2 norm squared of the vector x minus y. Here are the two inequalities. The inequality due to convexity is applied to x of k and v of k. F of x of k is greater than or equal to f of v of k plus the inner product between the gradient evaluated at v of k and x of k minus v of k. The inequality due to the assumption that f has a Lipschitz continuous gradient tells us that f of x of k plus 1 is less than or equal to f of v of k plus the inner product. The gradient vector is evaluated at v of k, and then here we have x of k plus 1 minus v of k. Then we have this term, L over 2, the L2 norm squared of x of k plus 1 minus v of k. Move f of v of k to the left-hand side. We get, regarding this inequality, move f of x of k here and move this term to the other side. We get f of v of k minus f of x of k is less than or equal to the negative of this term. Rather than having a minus sign, I will write the inner product of the gradient vector evaluated at v of k, and I write here v of k minus x of k. Add these two inequalities, we get f of x of k plus 1 minus f of x of k. This left-hand side is upper bounded by the inner product of the gradient vector evaluated at v of k and x of k plus 1 minus x of k. We also have this term here. Now repeat the same steps. Rather than using the vector x of k, we use x star, a point at which f of x attains its minimum. When we do so, we get another inequality, which is f of x of k plus 1 minus f of x star less than or equal to the inner product of the gradient vector and x of k plus 1 minus x star. This term remains intact because it does not contain x of k. Let's do a minor modification to this inequality. The left-hand side can be rewritten as f of x of k plus 1 minus f of x star minus, between brackets, f of x of k minus f of x star. We can also subtract and add x star in this bracket. Let's define alpha of k to be f of x of k minus f of x star. Using this definition, this left-hand side becomes alpha of k plus 1, and that left-hand side becomes alpha of k plus 1 minus alpha of k. These are the two inequalities we have developed. Recall that in the accelerated gradient descent algorithm, there is a sequence of scalars, g0, g1, g2. It's time to employ this sequence. We multiply this inequality here by gk minus 1. Then we add both inequalities. We get g of k minus 1 alpha k plus 1 minus gk minus 1 alpha k plus alpha k plus 1. Combining these two terms, the left-hand side becomes gk times alpha k plus 1 minus alpha k times gk minus 1. What about the right-hand side? These two quantities are the same. The first inequality is multiplied by gk minus 1, and then it is added to the second inequality. This L2 norm squared times L over 2 gets multiplied by gk. The inner product of the gradient vector and x of k plus 1 minus x star is multiplied by gk because this inner product is in both inequalities. The inner product of the gradient vector at v of k and x of k minus x star is multiplied by gk minus 1. After doing this weighted combination of both inequalities, we get this inequality here. Note that we are implicitly assuming that gk is greater than 1. If gk is strictly less than 1, gk minus 1 is negative. If it's multiplied by an inequality, it will reverse its direction. The assumption here is that gk is greater than or equal to 1 for every non-negative integer k. The algorithm itself starts with g0 equal to 1. When we come to the design of sequence G, we should show that gk is greater than or equal to 1 for every k. Reaching this inequality, multiply both sides by gk. Every gk here becomes gk squared, and every gk minus 1 becomes gk times gk minus 1. There is a missing alpha k here. Recall that alpha k is the discrepancy between the value of the function after k steps or k iterations and the minimum. It is this quantity that we need to show that it is upper bounded by some positive constant divided by something like k squared. In gradient descent convergence proofs, we typically have or try to have a telescopic series. We have here gk squared times alpha k plus 1, and here we have alpha k. If we are interested in having a telescopic series on the left-hand side, we need this product here to be equal to g k minus 1 squared. Here we have a function of k, and there we have the same function, but k is replaced by k minus 1. Sequence G is designed so that we exactly accomplish this. Sequence G satisfies that gk minus 1 squared is equal to gk times gk minus 1. as we have seen on the previous page, to get a telescopic series, we will impose this condition here, which implies that gk squared minus gk minus 1 squared is equal to 0. This is a quadratic equation in gk. Solving it, we get the update equation for gk. We have two solutions, but of course we want gk to be positive. In fact, we want gk to be greater than or equal to 1. So we use the positive solution. gk is equal to minus 1 over 2, that's 1/2. And then under the square root, we have 1/4 minus gk minus 1 squared. G of 0 is equal to 1. Can we show that gk is greater than or equal to 1 plus k over 2 for every non-negative integer k? Yes, we can prove this using induction. Suppose that this inequality is true, and it is true when k is equal to 0. What about gk plus 1? According to the update equation, gk plus 1 is 1/2 plus the square root of 1/4 plus gk squared. It is assumed that gk is greater than or equal to k over 2 plus 1. Then gk plus 1 is greater than or equal to 1/2 plus the square root of 1 over 4 plus the square of this quantity. This square root is greater than or equal to the square root without the 1/4. This is 1/2 plus k over 2 plus 1, which is k plus 1 over 2 plus 1. The desired result. Sequence G starts at 1. It's an increasing sequence. gk is superior to k over 2 plus 1 for every non-negative integer k. And this is the expression that we have seen in the accelerated gradient descent algorithm to update gk minus 1 and obtain gk. The motivation behind this choice is that we have in our convergence investigation alpha k plus 1 multiplied by gk squared minus gk minus 1 times alpha k. It is alpha k that is hopefully upper bounded by a positive constant over something like k squared. We already have alpha k plus 1 and alpha k. This is gk squared. To have something telescopic here, this should be gk minus 1 squared. Based on this, we know how to update sequence G. We also have this very important bound. Why is this bound important? I'm getting ahead of myself. If gk squared alpha k plus 1 is shown to be less than or equal to some positive quantity, then we can divide by gk squared. gk is greater than or equal to k over 2 plus 1. So 1 over gk is less than or equal to 1 over k over 2 plus 1. 1 over gk squared is upper bounded by 1 over 1 plus k over 2 all squared. And this is exactly the result that we are interested in. Let's go back to our inequality. Rewrite the update equation for vector x such that we obtain an expression for the gradient vector evaluated at v of k. X k plus 1 is equal to vk minus eta times the gradient vector. So the gradient vector is minus 1 over eta x of k plus 1 minus vk. We can insert this here in the right hand side of the inequality. This term is here. After replacing the gradient vector in this term, let's subtract and add vk in this bracket. We get x of k plus 1 minus vk plus vk minus x star. This term here becomes minus 1 over eta gk squared. Then the inner product of vector x k plus 1 minus vk with itself. This is the L to norm squared of x of k plus 1 minus vk. Note that gk squared outside the L to norm squared can enter inside as gk. We can combine the two terms with the L to norm squared. The outside factor here is L over 2 minus 1 over eta. Recall that eta is strictly positive and is less than or equal to 1 over L. Multiply both sides by 2 and then take the reciprocal. 1 over 2 eta is greater than or equal to L over 2. Subtract 1 over eta from both sides. On the left hand side, we get minus 1 over 2 eta. This implies that this bracket here is upper bounded by minus 1 over 2 eta. We make use of this upper bound. This is the inequality that we currently have. A and B are two n-dimensional vectors. The L to norm squared of A minus B is A minus B transpose times A minus B. This is A transpose A, the L to norm squared of A, B transpose B, which is the L to norm squared of B, minus A transpose B, minus B transpose A. These two inner products are equal. Both are equal to summation I from 1 to n, AI bi. AI is the ith component of vector A, bi is the ith component of vector B. So the L2 norm squared of A minus B is the L2 norm squared of vector A plus the L2 norm squared of vector B minus 2A transpose B. Rearranging the terms, we get that 2A transpose B minus the L2 norm squared of A is equal to the L2 norm squared of B minus the L2 norm squared of B minus A. If we look to the right-hand side of our inequality here, pay attention to the vector Vk minus xk plus 1. It appears here in the inner product, and it is also here in the L2 norm squared. This term can be written as minus the L2 norm squared of gk divided by the square root of 2 eta. This scalar is multiplied by the vector Vk minus x of k plus 1. Let this be vector A. We can write this part as square root 2 eta over gk times vector A transpose. This term here can be written as 2 times vector A transpose, and we have 1 over 2, 1 over eta, square root 2 eta over gk, and then this bracket here. To match what we have in our identity, this is vector B, the vector between brackets divided by gk, the square root of 2 eta. Now our upper bound is in the form of 2A transpose B minus the L2 norm squared of A. In this expression, we have gk minus 1 squared, which is equal to gk times gk minus 1. We can take gk as a common factor to eliminate this guy here. Vector B is 1 over square root 2 eta times gk vk minus gk minus 1 times vector xk. We have minus gk times x star plus gk minus 1 times x star. So we have minus x star. This is vector B. We need vector B minus A. Let's rewrite A as 1 over square root 2 eta between brackets vector Vk multiplied by the scalar gk minus vector xk plus 1 multiplied by the scalar gk. If we subtract this from this expression, these terms go away. We have 1 over square root 2 eta gk xk plus 1, then this part here. As an upper bound, we can use the L2 norm squared of vector B minus the L2 norm squared of vector B minus A. We also have the difference between two quantities. If we are interested in having a telescopic series on the right-hand side, if this vector here is beta k, then we need this vector to be beta k plus 1. Beta k is gk vk minus gk minus 1 xk minus x star. Beta k plus 1 is this vector here, and we can obtain another expression for beta k plus 1 by replacing each k here by k plus 1. So beta k plus 1 is equal to gk plus 1, vk plus 1, minus gk plus 1, minus 1, xk plus 1, minus x star. This is equal to this expression here. Minus x star goes with minus x star. Then the remaining terms provide us with a relation between v of k plus 1, x of k, and x of k plus 1. If we put vk plus 1 on one side, the other terms on the other side, we now have an update equation for vector v. During the kth iteration, we can use xk and xk plus 1 to obtain vk plus 1. Recall that the first step in the kth iteration in the accelerated gradient descent algorithm is to obtain xk plus 1. Specifically, xk plus 1 is v of k minus eta, the gradient of function f evaluated at v of k. After obtaining xk plus 1, we obtain gk plus 1, and then we obtain vk plus 1. This is our inequality now. It has been engineered so that we have a telescopic series on both sides. Let's sum both sides from k equal to 0 to k equal to n minus 1. On the right-hand side, we have 1 over 2 eta. If k is equal to 0, we have the L2 norm squared of vector beta 0 minus the L2 norm squared of vector beta 1. If k is 1, then we have the L2 norm squared of vector beta 1 minus the L2 norm squared of vector beta 2. Then k is equal to 2, then 3, all the way to n minus 1. All these terms cancel, and we have two survivors, the L2 norm squared of vector beta 0 and the L2 norm squared of vector beta n. The L2 norm squared is non-negative, and so we can do further upper bounding, just keeping the L2 norm squared of vector beta 0. Like what we did here, we can also do the same on the left-hand side. It is also a telescopic series. If we do the summation, there will be two survivors. We have jk squared alpha k plus 1 when k is equal to its highest value n minus 1. We have gn minus 1 squared alpha n. Then we have gk minus 1 squared alpha k when k is equal to 0. This is alpha 0, but if we put k equal to 0 here, it is like we have g of minus 1. And what is g of minus 1? Recall that gk minus 1 squared is equal to gk times gk minus 1. If k is equal to 0, we have g0 times g0 minus 1. But g0 is equal to 1, so this is equal to 0. Our inequality becomes gn minus 1 squared alpha n less than or equal to 1 over 2 eta, the L2 norm squared of vector beta 0. Alpha n is the value of the function evaluated at xn minus the minimum value f of x star. Beta k is this vector here. So beta 0 is g0, which is 1, v0 minus g0 minus 1, x of 0. So that's 0 minus x star. During the initialization, we set v0 equal to x0. So this is x0 minus x star. F of xn minus f of x star. That's the difference between the attained value after n iterations and the minimum of the function. This difference here is upper bounded by 1 over 2 eta times the L2 norm squared of the vector x0 minus x star. This is divided by gn minus 1 squared. We proved that gk is greater than or equal to k over 2 plus 1. 1 over gk is less than or equal to 1 over k over 2 plus 1. 1 over gn minus 1 is less than or equal to 1 over n minus 1 over 2 plus 1. If we multiply the numerator and denominator by 2, we get 2. The denominator is n minus 1 plus 2, that's n plus 1. Thus, 1 over gn minus 1 squared is upper bounded by 4 divided by n plus 1 squared. F of xn minus f of x star is upper bounded by 4 over 2 eta, that's 2 over eta times the L2 norm squared of x of 0 minus x star divided by n plus 1 squared. In the ordinary gradient descent algorithm, where xk plus 1 is equal to xk minus eta times the gradient evaluated at xk, we get n here. Now we obtain xk plus 1 using the v vectors, which are obtained in this way. Both expressions have been obtained in the attempt to construct telescopic series in the analysis of convergence.